right, here we are back for another Physics 4C lab. We have been looking at lenses in class, and we are ready to do some measurements of some lenses. What we want to be able to do is go in and measure their focal lengths. So we want to be able to take some lenses and measure these sorts of properties. So we want to measure their focal lengths, and we also want to do some lateral magnification measurements. Now, the lenses we look at are going to have a particular focal length to them. The magnifications are going to depend on where things are placed. So that's going to depend on object placement. But the lenses themselves, that's an intrinsic property, is this focal length. Now the formulas that we've been looking at in class, for the focal length of a lens, 1 over the focal length is equal to 1 over the object distance plus 1 over the image distance. And remarkably enough, that formula works for both converging and diverging lenses. Remember in class, we've talked about 2 different classifications or 2 different categories of lens. There are converging lenses where the light leaving the lens is either being brought together or it's more brought together than the light as it entered. So the example we showed was a lens a little thicker in the middle. If we have an object with light spreading out as it approaches that lens is going to tend to bring the light together. Now, there's no guarantee that the light will converge. There's no guarantee it'll converge enough to form an image. But as long as the object is placed far enough back away from the lens, then the converging lens will be able to bring the light together. In either case, it's going to end up converging. Diverging lenses, on the other hand, we've seen in class, those are the ones that are thinner in the middle. And as a result of refraction at the 2 surfaces, the light that spreads out as it approaches a diverging lens, well, when it goes through the lens, it's just going to spread out more. So that's going to become more spread out. Now, with a converging lens, it's going to be easy enough if we take one of our samples. Now, we're going to have 2 samples for converging and 1 sample of diverging lenses, and they're around here somewhere. Let's see. Here's a couple of the converging ones. So here's a converging one. I've got it in the tables here. So a couple of converging ones with different focal lengths to them. And then here is a diverging lens. And you can see this diverging lens, it's thinner in the middle. All right, so that's what the samples themselves look like. Let me grab these. I guess I'll take these with me. Those look like they might be useful to be able to talk about what's going on here. So in my diagram, for the converging lens, I'm going to draw a line that represents the placement of the converging lens. If you draw it with a little bulge in the middle, that's okay, but when you start doing ray diagrams, it's going to be easier, it's going to be cleaner to be able to do the ray diagrams, which is drawing one straight line. And so here's an object that I've placed, and here is the placement of the converging lens, right here. And what I've done is I've identified a focal point on either side of the lens. What we've seen in class is that thin lenses are reversible, kind of a remarkable property. I remember when I was in 2nd grade or whatever, when I first got my glasses, turning my glasses around and hey, they work backwards. And it does turn out that the 2 surfaces are going to have different curvatures on either side, but the combination doesn't depend on which order that curvature takes place. Anyway, they're going to have a focal point on either side. When we do the ray diagrams, we start with something parallel coming in, and then the light that's refracted in the lens is going to pass through the focal length on the other side. A path of light headed right towards the center of that lens is just going to go straight through in the thin lens approximation. So it gets refracted a little bit on one side, but it gets unrefracted by the same amount on the other side, and it cancels out. So it gets shifted a little bit, but in our ray diagrams, we ignore that small effect. And then finally, if we take something through the focal point on the way in, it's going to come out parallel. So make sure you're learning how to do these ray diagrams. Make sure you're staying caught up with everything. I am one of your, I'm a lab partner in your lab group. And so, and I'm a useful lab partner because I'm staying caught up in all of the class, all my lectures I'm staying caught up with, I'm doing all my homework. I understand how this works because I'm staying caught up. So make sure you're a good lab partner too, that you can contribute to the discussion within your lab group. All right, here's my real object, and the real object has been placed outside the focal point. That's giving me a real image. So what we can do with these lenses, and we'll see the equipment we're going to be using for that. What we can do with these lenses, in fact, let me just grab it. I can show you guys this. Let me get one more piece of equipment up to the front. Here it is. And so this is what the equipment looks like. There's a table, and along, I don't want to break the lens, the table along the platform here, it's got basically a meter stick. So there's a meter stick with all of these centimeter numbers listed on here. And what those centimeter numbers are going to allow me to do, it's going to allow me to keep track of all the object and image distances. And so what I've got set up, I can set it up like this. I don't have the object set up yet. I was just looking at images from out of doors right now. But I do have the lens support. So here's a lens support, and here's a screen. So the screen is used to create images. So if I can place the screen at the location of the image, then I can see it with my eyes. So I can see the light coming off of the screen, and that's how we're going to do those measurements. So again, that's how we're going to place our lenses and locations for the screen. So for the converging lens, what I'm really after here is I just picked some kind of an arbitrary object distance. So we want to try different values of object distances because we want to see if we keep getting the same focal length. What we're guessing is, again, our objective for the day is we've been assigned by the company we're working with. We've manufactured some lenses, and we've been assigned to go in and check their focal length. So we've got these lenses, or maybe we found some lenses lying around, and we thought, these would be useful. Let's go in and measure their focal lengths, and we'll label them and put them in the right drawers so that people, when they come, will know what those focal lengths are. All right, so the data tables for today, I want to be able to go in and measure object distances and image distances. So object and image distances are going to be enough to be able to go in and calculate a focal length. Same as in the homework, right, that we've been doing because you guys are staying caught up in the class. So I'm going to be able to measure a focal length from that. Now, along with the object and image distances, what I also want to be able to measure is I want to be able to measure the object and the image heights. So what I can do is go in and measure the size of the object, and we'll see what that looks like, and then measure the size of the image. And also, so these are the direct measurements. So let me get that labeled. That's actually useful. Let me get something red to provide a little contrast. So before we were saying, let's always go in and identify what are the direct measurements that we're making. So the direct measurements we're making here today are DO, DI, HO, HI. Once I have DO, DI, HI, HO, HI measured accurately, that's going to be enough to carry out the calculations for focal length and the calculations for lateral magnification. So those last three columns are going to be calculated values. Now what we're expecting is that we're going to try different values of DO, we'll get different values of DI and HO and HI. But what's going to happen is when we look at our focal length, we're guessing that the focal length numbers will look pretty similar. If they don't look pretty similar, our first concern is that we've made some kind of a mistake. Okay, we've made an error of some sort where we're not getting the same focal lengths because they're so different. And that's always something to watch for in lab, right? if the numbers start to go kind of crazy from one run to the next, don't finish taking all the data. Stop and see if you can figure out why the numbers don't have the consistency where you would expect it to be. So, and this is a column where we expect those numbers to kind of be very similar to each other. Now over here, the magnifications can actually vary. And I hope we've seen that in the homework problems and the examples in class. But I've got two different formulas for magnification. Officially, magnification is this, right? It's how big is the image compared with the object. Now, that would mean I put in the HO, I divide through by the H. I put in the HI, divide through by the HO. That's going to tell me my magnification. But what we found in lecture was that based on these ray diagrams, there are some similar triangles right here and here. There's a right triangle. Let me just draw that in. There are similar right triangles here and here. Maybe you just remember from lecture. And the ratios of the sides tell us that H over HO really should be the same thing as DI over DO. So we can calculate the magnification either way. What we're doing in lab is we're doing both. So we're going to measure HI and HO and determine the magnification from that. And then we're going to go back and measure DI and DO, or put those numbers in, and check and see if the magnifications match. So what we're guessing here is that at each one of the runs that we do, these two magnifications should match pretty well, and these should match pretty well, and these should match pretty well, and those should match pretty well. So we're looking again to see if we can find some consistency in the magnification values that we're coming up with. All right, so the converging lens, I'm going to say that should be pretty straightforward. Now, one thing that always comes up with lenses, erase that. One thing that always comes up with lenses, and we've talked about this in class, is the formulas are easy, except you got to keep track of the signs. So the formulas are deceptively simple. The math is not that difficult, but the problem, or not the problem, the feature, the whatever, is that DO could be positive or negative. DI could be positive or negative. F could be positive or negative. Now, again, we're looking for consistency between those. A positive object distance tells me that the object is real. A positive image distance tells me that the image is real. Now, what does real mean? In this particular setup, which I'm going to say is the simplest setup we can see for any type of lens, converging lenses, I'm going to say, are easier. And this particular setup, from real object to real image, that's about the easiest ray diagram to draw. And what we see in this case is, if I call these three paths my object light is the light headed towards the lens. And in this case, it's a real object, and that object light is spreading out. Now, what happens with this particular setup of my converging lens is the light on the other side, which is I'm going to call my image light, consists of these three paths. So now I've got, once the light's past the lens, each of these paths is now redirected. And so this pattern is now what I'm going to call the image light. This is the light that makes up the image. And it converges, or it comes together at one particular location, and that's going to be the location of the image. So when we have a nice, sharp image on the screen, we can measure that distance. That's what we're looking for. Now, a little bit of this lab comes down to moving the screen back and forth and finding out where the image is as sharp as possible, right? So it's not like there's just one location where you can see the image and then all the other locations it's just a blur. What happens is the image gets sharper and sharper until you cross that image point, and then as you keep moving it gets a little more blurry and a little more blurry. So it's kind of a back and forth technique until we can get the image as sharp as possible. We'll see that when we do the close-ups. All right, converging lens, that's the easy one. This one I'm hoping isn't too difficult. Now remember, there's two samples. There's going to be two sets of data that you want to work from for that. Now on the diverging lens that we have, and so one of our samples is a diverging lens, that's going to be hard because there's no way with a diverging lens that we can start with a real object and get a real image. That's just not going to happen. And so what we have to do is we got to use multiple lenses. I can't just use one diverging lens by itself. I got to use an additional converging lens to get this focal length. Now, it turns out we can put these in either order. We can either have a converging lens first, followed by a diverging, or we can have a diverging lens, followed by a converging. The setup I'm going to use today is I'm going to start with having an object out here, passing it through a converging lens. So it's kind of what we've already done. So when we want to measure the diverging lens, we set up everything like we did initially, but what we do is this. Instead of letting the light come together and form this real image, we're going to place the diverging lens here. We're going to place the diverging lens at a location upstream from where that real image was being formed. Now I've stretched this out a bit on this other diagram. So here is the converging lens. I've got an object over here. I'm going to follow just these three paths and follow them out and say that the converging lens by itself formed an image at this location. Now what we're going to do then is we said we wanted to place a diverging lens ahead of that image so that the light never actually comes together at that point. We're going to place the diverging lens there. The effect of the diverging lens is going to take light that was, the light was coming together, but instead we put a diverging lens there. The diverging lens diverges it a bit, but we have to make sure that with our placement we don't diverge it too much. The diverging lens will make the light come together farther downstream, is the idea. So that's what we're doing with this. So we're going to have this light come out to this location as if it's coming to this point, but with the diverging lens in place. Those light paths are now going to head off towards a new location. Now, for this last image of the diverging lens, I haven't drawn all three lines. I think that it may just make it more confusing. Go back and try that and see on your own what that would look like. But what we're working with here is, this is now what we consider to be a virtual object. Now, why is that a virtual object? It's because the object light the light that was headed towards that diverging lens is not spreading out as it would from a real object. It's already coming together. And so since we have light that's already coming together, this is what we consider to be a virtual object. And that says when we go in and measure the object distance, we have to put a minus sign on that. So we got to get a minus sign on that object distance in our data tables. Now you might think, well, if I get the sign wrong, it'll just show up as a reversal of sign in the focal length. But that's not true. If you look at the formula here, if I get the sign wrong on DI, or I'm sorry, on DO, but I get the right sign on DI, that's not going to change the sign on F necessarily. You're just going to get completely different results. So you really do have to pay attention to the sign. One thing I forgot to mention earlier, too, let me mention it now. is that another place where the sign is going to become important is back with our so-called easy example. I've got an HI here and an H, or an HI here and an HO here that are in opposite directions. And so I'm going to have to list one of those HOs or HIs. One of those is going to be positive and one's going to be negative. Now, typically, we think in terms of if it's a real object, we go ahead and, even if it's a virtual object, go ahead and list this one as being positive. But if I list HO as a positive value, I've got to make sure HI is negative. Okay? So that has to be the case. So when I go in and measure these magnifications, all these magnifications for the converging lens, they're all going to be negative values because there is an inversion taking place for the setup that we've got. Now in the diverging case, if we look at magnification, notice that from the ray diagram for the diverging case, the HO and the HI, they're in the same direction. So I could list this as a positive value and this also as a positive value because the diverging lens by itself is not creating an inversion. Notice that once we move on to the diverging lens, the converging lens is out of the picture. There's none of the DOs and DIs from the converging lens. We're not using any of those. What we are using are DOs and DIs where the DO and DI are measured relative to the diverging lens. So once we've moved on to taking measurements of the diverging lens, everything is based on the placement of the diverging lens. Nothing is based on the placement of the converging lens. Okay, so in this one, the DO will be negative. That's a virtual object. The DI will be positive because the image is real and it's going to show up on our screen. So what that means is we're going to have to move the screen back and forth. We're going to have to move the screen to here to find out where the virtual object is. And when we do that, we're going to have to take the diverging lens out. So we remove the diverging lens. We place the screen here, identify the location of the virtual object, but then we put the lens back in. Now when we put the diverging lens back in, that's going to be blurry. And we'll know that at that point I got to move the screen back until it comes into focus, and that's going to be the location of the real image. So, and that's going to give us the DOs and the DIs. So that's a more difficult setup for sure. But what we can do is the data table is going to look the very same. So again, the formulas are the same, whether it's converging or diverging. In fact, the formulas are the same for mirrors. Mirrors, converging and diverging. Lenses, converging and diverging. They all use the same formulas. So they all have these same formulas to them, but we've got to keep track of the signs. Signs are going to be important. Okay, so that's all of the formulas leading into this. Now, I think what we can do, let me see if I can just segue into this. What I'm going to do is I'm going to pick this up. I'm going to move this over to the table. I am going to re-angle. Give me just a second here, see if we can re-angle the camera. I think that worked. Okay, let me make this a little more close up. And I guess we can't do that. We gotta leave more. This is a broader setup. So let's get something like this. That looks pretty good. And what we can do then is this. So here is kind of the setup that I've got. And in fact, let me do this. Let me see if this will work, just to show you how these lenses work. I am going to try opening up one of the blinds. So I just went back to the lab room. I'm opening up the blinds. And what I want to do then is, I don't know if you can see this, but what I've done is I'm looking out the window. And let me turn the lights off in the room. So I'm going to turn the lights off in the room. And I don't know if you can see this, but Let me see if I can get a close-up of what's going on here. What I've done is opened up the window. Light's coming in from outside that window. It's going through that lens. And what we should be able to see on this is an image. Look at that. What is that an image of? And that's the building across the way here. That's the Forum. So let me just turn this around. Okay, nobody get nauseous. I'm looking around the physics lab room here. That's what's outside the window. Those are my papers on that desk. There's what's outside the window. And light from that, oh, look, it's the physics lab room. Light from that is coming in through that lens. Here we go. And creating that image. Now, is that image right side up or upside down? And that looks kind of upside down to me. It's in pretty good focus. So what we would do then is we could measure some DOs and DIs. Now the DO for this one is going to be really hard to measure. So we typically don't use this as more of a demonstration more than one of our measurements. But the idea here is we could measure a DO, which would be all the distance out to that building, and then we could measure DI. DI would be measuring this distance right here. So we could measure between that lens and the screen. And we have a DO and a DI. Now for the HOs and the HIs, I could measure, I could go to that building and measure, I don't know, the bricks or that strip of concrete, and then come back over here and measure the strip of concrete here, or measure all those bricks. That would be easier. So we could measure the distance on those bricks, go out here and measure how big those bricks really are, and see what the magnification is, right? So that's kind of the idea. Now, most of our measurements are going to come a little differently from that. What I'm going to do, let me grab a couple of items here. One of the items that we are going to introduce now is, I hope you guys can see this. This is our object. It's a plate with a couple of arrows in it, so we can keep track of inversions. And I'm going to place that onto this platform. And then also what I need is, I'm going to get a light bulb. I'm going to get a light bulb added in. I've got a socket here. It looks a little dangerous, but I'm used to the risk. Okay, I'm going to plug in that light bulb. I'm going to get the light bulb set up in front of that screen. I'm going to plug it in, and I'm going to turn it on, and it's really bright. So I'm hoping you guys can see this. So I'm going to grab the camera and take a look at this. I'm going to go close the blinds too. So, and we'll see what we've got. All right, let me go close the blinds. So this light bulb was unable to compete with that bright light from outside. So now what I've got instead, let's see if we can get this, is there. In fact, let me do this. Let me make a big image so we can make sure we can see it. So what I'm doing is just playing around with the object and image distances. I'm adjusting the heights on the lens and the screen so that, and now I'm going to come in and try and do that last fine tuning. I'm kind of going back and forth. I'm trying to find out where that image, see how it goes blurry in either direction. I'm going to try and find out where the image is as sharp as possible. That's about the best. So I may need to put my own lenses back on.
to get a good view of this. But in any case, what I'm going to do, let me show you guys. And so here's the setup. I have a light source. Let's go in and see what that object, see what the object looks like? It's a couple of arrows that are crossed. Maybe you can see them better from the other side. There's the placement of the lens right there. And then here is the screen, and that's what the screen looks like. Now I haven't got it quite centered on the light source, so it's not uniformly bright, but that's basically the idea, is to do something like this. Now once I've done that, I'm going to come back. Unfortunately, let me see if there's a place I can set this. I think I'm going to have to go back up to this perch. Let me pause this just for a second. So I'm thinking maybe the easiest way to show this is, so the DO is going to be between where the lens is, here's the lens location, and where the object is. Now the object is actually that piece right there. So the object distance is between those two devices. The light source is just a light source. It's separate. It's illuminating the object, but the object itself is that plate. And then the image distance is going to be measured here. Now to get the object and image heights, what I need to do is get out a ruler, and I'm going to do that, and measure the size of that arrow pattern. Now I could measure the whole length, or I could measure just the tip of the arrow. It depends on what's going to be most useful. For the setup I have right now, I can see kind of the entire arrow length. So I'm going to measure the entire length and find out how many centimeters one of those arrows is here. And then I'll compare it with the arrows over here. And from that, I'm going to be able to come up with magnifications. Okay. So that's what the setups look like. We're going to do several of these. Now, we want to come back and take a look at the diverging setup also. All right, so I've got this set up now with the converging and diverging lenses. And here is the converging lens here. Here's the diverging lens. And here is that real image coming off the diverging lens. Now, to do this measurement, we would need to have a DO and a DI. Now I've got the DI. I can look at the ruler set up on this optical bench and measure the DI here. And I can measure the HI. Notice that the image this time is so large that, let me show you here in a little more detail. The image is pretty large. All I can see is just that tip of the arrow, but that's fine because I can come back to here. Actually, not to there. Never mind. The tip of the arrow, I can get the image height, and I can get the DI from between the lens and that location. Now, what I've got to do is I've got to go back and find out where the object is located. Currently, I've got light coming through this converging lens, headed towards the diverging lens, but the diverging lens is placed in front of that object, so I'm going to have to remove that. I'm going to go ahead and remove it right now. So let me do that. I'm going to take this diverging lens and move it out. And notice when I do that, what I've got on my screen now is just blurry. So what I got to do is bring that in closer to find out where the image was located. And I'm guessing it's about as sharp as it gets right there. Okay, so that's where the virtual object is located, and I can only see that virtual object because I've removed the diverging lens. Now what I can do now is take that measurement between those two supports. What I've got is the placement, the lens, the diverging lens went right there. So I've got a ruler in there that I can measure, and it looks like it's 4 or 5 centimeters. So that looks like the distance of the object. Okay. So again, let me show how that worked. What I'm going to do is I'm going to put the diverging lens back in place. So there's my diverging lens. With the diverging lens back in place, the image on the screen now has gone fuzzy. I don't know if you guys can tell that. So I'm going to move this farther out until once again I'm back to a really sharp image. So that was going from the object distance to the image. Now I've got the image distance, and that's how it works for the diverging lens. So any questions you guys have, stop by office hours, stop by lab hours, and let's get those answered. But that's kind of what the setup looks like. And then we just do a large number of these measurements and then take a look and see what we've got with our focal lengths and with our magnifications.